So now we're going to look at a few examples of how to use Green's theorem. So our first example here is to find the work performed by a vector field. Our vector field is vector f of x and y is y comma x. So the work performed by a vector field moving a particle along the triangle with vertices at 0, 0, 1, 0, and 1, 1. Well, if we're thinking about trying to use Green's theorem on this problem, a couple of things to think about. First of all, we're asking to find the work done. So remember that work is the integral along the curve C of vector field f dot dr, where r is position vector. And remember that that could also have been written the integral over curve C of m dx plus n dy. So those are the two integral forms for finding the work done by a vector field. And so we need to check our assumptions or hypotheses for Green's theorem. Okay, so as we start thinking about whether these hypotheses are satisfied, one thing to notice here is I've drawn our region R. I have my triangle with vertices at 0, 0, 1, 0, and 1, 1. And the particle is moving around that curve, the edge of that triangle, the sides, in a counterclockwise fashion. So I've also got there my arrows indicating the direction in which the particle is moving. So our first assumption is my region R? So my region R is that region inside the triangle, highlighted in yellow, and I've annotated that with an R. Is that region bounded by a piecewise smooth curve oriented counterclockwise? And the answer to that question is yes, it is. So our region R is bounded by a piecewise smooth curve oriented counterclockwise. So that's good. The first hypothesis for using Green's theorem has been satisfied. Now remember, the second hypothesis has to do with m and n. So if we look at our vector field here, our x component is m and our y component is n. So we're going to have to move on to the next slide, and what we need to know is if the partial derivatives of m and n are continuous on our region. So let's go to the next slide. And so here we're going to pay attention to the continuity of the partial derivatives. So recall that our m was y and our n was x, and they are polynomials. And what do we know about the partial derivatives of polynomials? They're also polynomials. Partial derivatives are also polynomials. And because that's the case, then polynomials we know are continuous everywhere. So therefore they are definitely continuous in an open region containing our region R are also continuous on any region. So Green's theorem does apply. Okay, so let's take a look at what that might look like. So what we have here is work is going to be the integral over curve C of m dx plus n. N is, let me fix that. N, we said for this problem, is actually x. So x dy. And that's going to be equal to the double integral over that region in the plane, the partial of n with respect to x minus the partial of m with respect to y, dA. So let's take a look at what those partial derivatives actually are. So the partial derivative of n with respect to x is equal to, let me fix that real quick, is equal to the partial with respect to x of x, so that's 1, and the partial of m with respect to y is the partial with respect to y of y, which is also 1. So my integrand here, when I use Green's theorem, actually ends up being 1 minus 1. So this is 1 minus 1, which is 0, as we all know. So my work is equal to, oh, that pen does not look good. That's because it's not the right pen. Let's fix that. Our work is actually equal to the double integral over my region of 0 dA. And if my integrand is 0, then we know that the limits of integration aren't going to matter. I'm not going to take my time to go ahead and figure out what that region is because my integrand is 0, meaning the work done is 0.